Well, let's start by talking about this assumption. So what I'm going to add is not too extensive beyond what I've written on the board. But the key thing is that if this is true, then we can write the velocity field in terms of the gradient of a scalar. Now one can write vector identities to show this. Basically you can say that the velocity field always consists of the gradient of a potential plus some component that's proportional to the local curl. If the local curl is 0, that means that what's left over is just this part. Furthermore, if you place some constraints on how much crazy stuff there is in a flow, if you say if there aren't weird point singularities or things like that, then not only can you say that this offers a possible solution for the velocity field, but it's in fact a unique solution for the velocity field. So if we say that the flow isn't rotating, I can describe this velocity in terms of this potential. If I then combine that with conservation of mass, conservation of mass says that the divergence of the velocity field is equal to 0. And if I plug in this expression, this tells me that del dot grad phi v is equal to 0. And I can then write that in terms of the Laplacian. So this is a more detailed vector proof, which I'm not going to get into. But if you're willing to buy this argument, I hope that you can then see next how adding this kinematic constraint to conservation of mass leads us to this point. This is now a Laplace equation for a scalar. It's an elliptic equation. It's linear. Because it's linear, it allows for superposition. Because it's elliptic, it's relatively well behaved to solve. This has a whole bunch of analytical expressions that we can solve by doing eigenfunction expansions. And if you want to solve this numerically, it's very straightforward. In fact, if you want to solve this numerically in Microsoft Excel, you can even do it in Microsoft Excel. You know, if I gave you a simple geometry that was was made up mostly of squares and rectangles and stuff, and I asked you to calculate it in Microsoft Excel, you can do it. So this is really a quite simple job. If you've taken anything and you've simplified it down to the Laplace equation, in a certain sense your analytical work is done, because a computer can do the rest without things getting too hairy. Okay. Well, the next question is, why might I think that this will be true? Or when might I think that this will be true? When is it reasonable for me to expect the vorticity to be 0? And so to address that, I want to take the Navier-Stokes equations and I want to put them in a slightly different form. This slightly different form is called the velocity-vorticity form of the Navier-Stokes equations. And it basically gives us a way of describing not how the velocity moves around as carried by the momentum, but rather how the vorticity moves around as carried by the momentum. And what this will do is it will allow us to take what happens to the vorticity and focus it on specific terms in the equations. And hopefully this will allow us to identify some key situations where we can expect the vorticity to be 0. Okay. Well, these are the Navier-Stokes equations. You'll note that there's no body force term. And I'm basically using this to describe the flow that I expect to happen outside an electrical double layer in a microfluidic system. Now I'm going to take the curl of this equation. And so I'm basically going to take del cross this term, del cross this term, del cross this term, and del cross this term. And when I take this curl, what I'm going to do is I'm basically going to take one of these terms and I'm going to make it go away. And then I'm going to take the other term and make it a little bit more complicated, but in a way that focuses my attention on a specific aspect of the vorticity. So, if I take del cross this term, this is a scalar. The process of taking the curl and the derivative with time, they're both linear operators and they commute. So the curl of du dt is equal to d du of the curl of u. And that means that taking the curl of this turns this into d omega dt. Similarly, if I go over here and I take the curl of this, I'm basically taking the curl of this scalar which comes out. I'm taking now the curl of the Laplacian of u. But the Laplacian is also a linear operator, and the curl is a linear operator, and the Laplacian and the curl commute. So the curl of the Laplacian of u is equal to the Laplacian of the curl of u. So because I have all these nice linear operators going on, this process ends up being straightforward. I take the curl of this, and this u also becomes omega. So those two terms are relatively straightforward. Now, if I take the curl of this term, what happens? It's 0. Why is it 0? Yeah, that's right. It's a vector identity that the curl of the gradient of any scalar is equal to 0. So this is true identically for any pressure field. And so that term just goes away. And then what I'm left with is now the curl of this expression. And this expression is now trickier because now this term is nonlinear. And so because this is a nonlinear term, when I perform this vector identity, I basically have to do the vector version of the chain rule, and I end up getting two different terms here. Now, this form of the governing equation is what we call the velocity-vorticity form of the Navier-Stokes equations. It's mathematically equivalent to what we showed before, but because it's expressed in terms of different quantities, it is convenient for different application of the boundary conditions. For example, if you have a lot of independent information about the pressure field, you can imagine that this form of the equation actually doesn't help you that much. If you know a lot about the pressure, you'd rather use this form of the equation because the pressure's in there. You can put it in and get some information. Now, there are two key things we can learn from this that are relatively straightforward and don't involve our studying anything in great detail. Well, maybe there are three things. I'm going to alternate back and forth between calling them two things and three things. Let's first look at the structure of this equation as compared to the structure of the Navier-Stokes equation. In a certain sense, I have three things that stay the same, right? Time change, a convective term that basically shows how the velocity convects gradients and momentum, and a diffusion term that shows how viscosity diffuses away concavity in the velocity distribution, or in this vector sense, the Laplacian, which is the sum of the concavities in the three different Cartesian directions. If I look down here, I have an unsteady term, a term that shows how velocities convect gradients in the vorticity. And here I have a diffusion term that shows how the viscosity diffuses away the Laplacian of the vorticity. But there's a key difference. Here I'm talking about momentum, and the way I keep track of the source term and the momentum is by looking at the gradient and the pressure. Where there's a pressure gradient, there's a body force, and that applies momentum. Here, I've looked at a specific aspect of the equation that takes this pressure part and makes it go away. But now I have this extra term. And this extra term is typically referred to as what's called the vortex stretching term. So now two things that I want to pull out of this. One of them is, how does the vorticity change when we start out with no vorticity? If I just have a puddle of water and there's no vorticity, I want to ask, what do the governing equations tell me about how vorticity changes? Right? If I look at this equation and I say my velocity is 0, how does the velocity change? Your answer is, well, this term's 0, and this term's 0, and this term's 0, so the velocity changes because there's a pressure gradient. So if I say at time t equals 0, the velocity is 0, it can change because of the pressure. If I tell you that there's no velocity now, that doesn't mean there's no velocity later. But now let's look at this equation. If I tell you at time t equals 0 that there's no vorticity here, which means this term is 0. There's no vorticity here, so this term is 0. There's no vorticity here, so this term is 0. This equation tells you that if there's no vorticity at time t equals 0, there will not be any vorticity later. That's what the governing equation tells you. Furthermore, the geometric structure of this term also tells you that if you have a flow that's strictly two-dimensional, the vorticity will point in one direction and the gradient of u will point in another direction, and these two tensors are orthogonal to each other. So if I have a 2D flow, there's no source term in the vorticity equation. And if I don't start out with any vorticity, the governing equation provides no means for vorticity being created anywhere. I can't just create vorticity inside a flow. And that is different from velocity. Like velocity appears if there's a pressure gradient, but vorticity doesn't. At least as described by the governing equation. So there are some two key conclusions. The first is that if there's no vorticity to start, no vorticity is created in a flow. And second, no vorticity is created in the flow. And again, these are conclusions that come from the governing equation. The governing equation says, in the bulk of the flow, vorticity is not created if I didn't have any to start. And even if I have some to start, as long as it's 2D, no additional vorticity is created. It's moved around, it's diffused, but it's not created by the governing equations.